moment staying with that mesh, but what I also want to show you with this example is how to generate diagrams, because this is a technique you definitely need independent whatever model you do. This type of results, they are very intuitive 3D. You also can get some survey, very useful, but mostly at the end to get some qualitative result, engineers display things in diagrams which looks like diagrams. Certain quantity here, other quantity there. So you should be aware how to generate that diagrams. And what may be useful is to display in such a diagram over the distance, over the length, the strain, the stress, and maybe the displacement. So let's generate diagrams with this information. So far, we used, I think, diagrams where we selected a point and then we saw some property for that particular point. This time, we choose a bit different type of generation of diagram. We define a line, and we want to have the information along the line, which actually provides also the information that we have on the x-axis, that line, spatial position, and then along the line we want to have the strain, the stress, the displacement. So, the easiest way to have a line would be selecting the edge of the beam, because this is already available by geometry. Maybe more interesting is, for symmetry reason, to have the line in the middle of the beam. So we could achieve this by already taking care about this when drawing the geometry, by drawing a segment line in a way the same way we did here for attaching the mass, but only for display purpose. That is an option. Sometimes it's a bit unsatisfactory, because if you have geometry, that affects also the mesh, you know, because that is a geometry which somehow is taken into account by the mesh, and if this effect is only for displaying, then it's nice to know there's another option, how you can define such a line. And let's start with this first. I think I already mentioned in results, all the simulation data is contained within a structure you found below data sheets. If you do several simulations, transient, stationary, parametric sweep, you find here different data sets. And you have to make sure when you display something that you select the according data set. That's sometimes a reason why things seem not to work. If you simulated transient and you still have selected the stationary data, then there will be nonsense. The reason why I talk now about this is you can also generate sub-data sets of that solution which we already have. And particularly you can generate a data set containing only data along a line. So that's what we want to do now. So we go to data sets, make a right mouse, and we do a cut line, cut out something in 3D. So this also exists in 2D and so on, a cut point in 1D, so there are several options you can do. Now we do a cut line in 3D. And we have to define the points of that particular line. There are different ways you can entry the information. Here we can work with the standard method, 2 points. So 1 point, starting point, the second point is just the end point, so to speak. Let's put reasonable numbers in here. X being 0 makes sense, then it starts here. And y, for y, we taking y is this direction, you see here on the coordinate system, so we take half the width. The width was b divided by 2. And for z coordinate, let's take the thickness d Of course, we also could take d half, then we would be in the middle of the beam. So for now, I'd be on the surface. Why it might not be a good idea to be in the middle? The neutral zone, maybe not so interesting. Let's put set to be on top of the bar. And the second point, here we should be at the end. Maybe it's enough to go to the point where we put the mass, which was L, otherwise we would have to we make the whole thing L to go to the place where we put the mass would be underscore M. Let's put L. Let's display the whole bar length. And here is also B half B, and also D. If you insert the numbers, of course, something can go wrong. It's nice to be able to plot, so you can check if this makes sense. The line is in red. So now we have a data set, all the simulated data, but only on that geometry. And with this thing, we can build our diagram. So how to build a diagram? The first step is always go to the main node resource, make a right mouse, and as a container we use 1D plot tool. And below the 1D group you have to decide what type of 1D. Previously we did one point plot. Now we make right mouse and take a line graph. We want to plot it along a line. And maybe I should have done it before. In the main container, we should change the data set from default study 1 to our cut line 3D. And now we even get immediately a result. Arc length in meter, you see this is the 40 centimeter and the total length was 43. We already have something on the y-axis which is called the displacement of the magnitude. Maybe we just keep this even, and what I recommend strongly, you can rename that things here. So over some time you forget what was plot 1, so maybe go to that thing and to label. I would also recommend to leave 1D plot, because it tells you how it was built, and then maybe put something which is helpful to make you understand what you plotted there. So solid disk is the displacement, the expression we actually use. So more plots. Instead of doing everything again, we can duplicate the diagram. So make a right mouse to 1D plot, and somewhere must be duplicate. So then we have to adjust things. First of all, we need to adjust the quantity we want to display. To display the Van Mises stress, either we go here in the browse menu and find whatever is suitable, or we already know from memory that was disk is always the mode, solid is always the mode, and then the quantity is MESS Mises. Let's see if it works or if I mistyped. I mistyped. So not double S, solid.mises. Now here we go. Let's have a quick check if that makes sense. The stress linearly increases towards the position where we connected it to the rigid base. What also makes sense, there is a region which has no stress. It's behind the mass. That was the point where we assigned the mass to. And what also makes sense, it increases linearly and has the maximum stress in the region of the attachment base. Yeah, let's do a third diagram by just maybe first adjust the label to MEMS, because it's not displacement, it's MEMS now. The solid actually is not really necessary, maybe it's even misleading, so I put the solid away here. Step up solid dystrophy on this. So one more, duplicate. And here I would like to plot the strain. Like I said, you could go in here and then if you find the right position, then you would find the according expression. In this case, it is called EEL11. That is strain, and in order to see it a bit amplified, I make it times 1E6 times 1 million. So let's plot this. Yeah. So I never taught mechanical engineering, but I know from the people, from the students who did this, there are equations, kind of simple equations for that beam problems, where you can calculate the strain. If you would use this analytic equation, then you could calculate exactly that line. Maybe some of you remember that it's possible. And what you would calculate with this analytic equation, of course, would be the maximum strain, which would, I cannot use the pen here, but I can show you anyway. Is there a, no, it's nothing. But I can misuse this device. With your analytic equation, you could calculate the stress at the point where you squeeze the beam. So that would be the extrapolation up here. So that would be what your numerical, the analytical equation provides you. What is interesting, if you trust the simulation, and I took some effort, it's realistic, is that in that region where it's most important, because it's maximum stress, the analytic equation fails. And particularly, you see here the real strain and also the real stress we saw it before is higher than what is given by the analytic equation. Somehow it then also goes down, but there is a maximum value higher than what you get from the equation. Practically, that would mean if you trust the analytical equation and you load it to a maximum value, it would be already in the region where it might be plastically deformed. It's just one of the examples where simulation helps you to get more realistic results than with simple equations. I mean, it's still nice to have such an equation which allows you in a simple way to calculate, but it has limitations because of the 3D structure, the way of the assumption that it's possible to derive such a simple analytic equation, particularly at the important region it breaks down. Yeah. One more thing I like to motivate with that little example here is the quantities we had looked to, the displacement, the stress and the strain that are typical parameter you are interested in mechanical simulations and also the evaluation of that. How that quantities depend on each other, is there any relation with this? If you remember, when we set up the model, the fundamental quantity we're solving for, heat problem temperature, here it was the displacement. How to find out afterwards, go to solid mechanics and scroll down. You know, if we set up the wizard, dependent variable, so we can look up here, that is what is solved for, the displacement field. It actually is a field, a vector field containing three components, x, y, z, or u, v, w. The thing I plotted for you is, so to speak, the magnitude of this displacement vector. So this is the basic variable calculated by COMSOL, that displacement thing. And with the other things we discussed, from that variable you can calculate all the other interesting things. So for example, how to calculate the strain and the stress from the displacement. Must be somehow possible. And there are some problems with it, or some not trivial things. I think we will not dive into this today, because we already did a lot of formal things, but I at least like to give you some motivation and point you toward the problem and why there is an issue. We talked about constitutive equations in electric. Ohm's law, the fields with material. This equivalent thing in mechanics I wrote here for a kind of simple case. This is mechanical stress. Let's put it like this. There are various types of stress. Von Mises says Piccola stress. Let's keep away from that for the moment. Stress is force on an area, like pressure. This is strain, and stress and strain are connected in the simplest case by Young's module. Probably you saw this. So that is the counterpart to Ohm's law, so to speak. So this is the constitutive equation, the material law. So it means if we have the strain, we can, with material information, calculate the stress. What you saw a second ago, what we actually calculate is the displacement. So there must be some connection between the displacement and the stress. It is simple, and that's how usually is talked about in the very beginning. If you discuss like a rod, maybe 1D rod, it has a length L, and if you pull on that in the direction of that rod, you make it longer by dl, or maybe instead of L we're using x to be the original size, and delta x would be how much you stretch it. Then this strain you would define to be delta x over x. That turns out to be a so-called engineering stream. Seems very straightforward to do. That would mean if we can calculate the displacement, you saw it here, if we have this, then we can calculate the delta, then we can calculate the strain. With material data, we can calculate the stress. Things become complicated if you consider more dimensions and more complex things like this. If I have something like this and apply a force, in general, I do something like this, or some banding. And maybe to explain this, I think I might use some slides just to explain the problem or motivate the problem which we later solve or give some solution how to handle it. This we finished. Some specialty in mechanics. Frame displacement strain. one thing we only have in mechanics is that we have different frames. We have one coordinate system for the undeformed geometry, which is called the material frame. And COMSOL uses the letters large X, large Y, large Z. Once you apply the force and acting mechanically on it, you get a deformed coordinate system, deformed geometry, the spatial frame. So this is only in mechanics. That's one of the reasons why it's a bit more, I think, complicated. Our displacement, U, which is simple as 1D, is connecting the undeformed geometry with the deformed geometry. This U is indicated here. You see, if that point in the geometry frame was originally sitting here, and then you're acting with force on it, it moves here, then the point are related by exactly the displacement vector. That's what we originally calculate. And the problem is, maybe I can try to sketch it in here. If you consider a little piece of length at that original point, and after applying the force, that original point gets stretched a little bit. Maybe I exaggerate here, but usually you don't double it, but it gets a bit more lengthy. Then the relation between that stretch and the displacement is of course not so simple as it would be in one direction. And particular, you can decompose that movement, so to speak, in two different types. One type of the displacement is as simple as this. The displacement just makes the thing longer, but another part of the displacement is just the rotation. The rotation part of the displacement, of course, doesn't stretch the whole thing. Both information is contained within the displacement, but for that reason, there is something which is relevant for our stretching and something which is not relevant because just a rotation. You could imagine, and I will show you an example in a minute, if you would have this and make a displacement by just rotating it. So you would not expect that there's any strain in it. Why should there be some strain? But obviously, just by rotating from here to here, you have a displacement. And that's what causes some problems. If the displacement is very small, whatever small means in detail, then what you learned, or most people are aware of, strain is delta x over x. Engineering strain works and is valid. But for larger displacements, that is the topic geometric nonlinearity. Then the concept breaks down and you need a different way to calculate the strain from the displacement. You cannot do it in such a simple way. So maybe at least you get some idea what problem occurs here, how to solve this and how to set up the equations to make that correct. We definitely don't do today, but I have another exercise in the first part of this, or actually the whole thing we can do now. So we do some more practical things, learn some more things, and this example also shows the problem. So it illustrates the problem. The solution for it we do next lecture. So what would be useful is the lab is called, or demo is called strain and large rotation, and there is a text file called dispxy. So if you load this text file, you can copy paste certain expressions which are otherwise maybe cumbersome to plot. to type yourself. The thing we want to do is shown here. Very simple from geometry. We make a square and we rotate the square by an angle of phi. This can be done with a rotational matrix. I'm sure you encountered this before. The coordinate system in the deformed geometry would be the system describing our rotated square. The undeformed geometry, labeled with large letters, would be the material frame. And coming from the undeformed geometry material frame to the deformed, if it's only a rotation, we can use here a rotational matrix. It's a 2x2 matrix with certain entries. If you do graphics, you probably know it from there. Or from, I think you are familiar with this type of thing, rotation matrix. That actually just means every point in the original frame is rotated by phi and plotted in the new coordinate system. So that's basically something we now implement in COMSOL. We use this rotational matrix for the rotation. And just for motivation, what we want to check now, we want to check the stress, could also check for the strain, or let's have a look for the strain, for this rotated geometry. Obviously, we wouldn't expect any strain or any stress. It's just rotated. That's something we want to analyze. So technically, we need to calculate the x and y coordinate in the deformed frame from the undeformed frame using that rotational matrix. So that's actually just writing the components out from that equation here. It comes from this line multiplied with this column provides you x, this y, this line, second line with this column provides you y. And the displacement, the relation between the two coordinate systems, u, what is calculated in COMSOL, would be like this. Does it make sense for everybody? U is x. X is this. So this is vector analysis. This vector u is x plus large X, but that goes in the wrong direction. You have to flip it. That is the reason why we have minus. Then we would have this vector plus this vector is this vector. This is how the coordinates and the displacements are connected. So we need such a displacement for the x coordinate and for the y coordinate. And from here to here is just subtracting another x, and I did the math. And these equations here I put in the file, which I refer to here in this thing. These expressions you find in the text file. So if you establish things, you can copy paste it from there. Otherwise, you would have to, or I would have to provide you this thing, and you type for minutes making mistakes. At least I would make mistakes. Let's go and set up that thing. And besides doing what I try to motivate, we also learn some other, I think, interesting techniques you can do with COMSOL. I should have started COMSOL before, or maybe I just use this one, make a new file. If you like to join me, then you are welcome. If you just want to have a look, it's also okay. We start with the wizard again. This time is a 2D problem with our square. It's solid mechanics. So we add it. Here again, you see the displacement field is what I showed you in that little diagram. That is what is calculated by some equations internally. Then we have solid mechanics with this dependent variable, and we study a stationary case. done. Yeah, we define two global parameters because only two we may type it in here. First of all, I like to have the rotational angle phi, phi, and by standard we use 10 degrees. Could change later. 10 square brackets open deck for degree, square brackets closed. It calculates in rad. So the number in rad should be like this, and if you like, you can put here rotational angle. Actually, maybe more explanation, it makes a little sense to you. Here we have the definition of strain for small movements, the engineering expression. And you can configure console in such a way that it uses this expression. It works if it's a small movement. Obviously, there has to be another way to configure it. As you might already guess, with a terrible name, Crane Lagrange strain something. And in order to see the behavior of the engineering strain and the Green Lagrange something, we built two squares to see them simultaneously. And the second square, we just move a certain distance from the first one, and for that we need a coordinate, which is called large x 0. So that is the origin, the x origin of that coordinate. So we move it by how much? 2 meters. You see a very large dimension. Why? Because we use the squares which come with 1 by 1 meter, so we need to move it away from the first one. That's it for the global parameters. Then let's build the geometry. Geometry, right mouse click, we use a square. Don't change anything, it's just for principle considerations. And we duplicate that square and shift it in the x direction here, base by x0. That's why we defined it up there. Let's see how it looks. Yes, so we got two squares. One we will configure with engineering strain, the other one. Yeah. So now we need to set up the variables, this x and this y, the components of the displacement. And this is something I think we haven't used yet. You can do in local definitions. So far we only did something in global definitions. So now we go to local definitions. There's not so much in here. We made a right mouse click and define variable. You can do a lot of things here. One of the things you can define variables, and in the variables we define our disps, or displacements. So, if you open up your text file I provided you in Moodle, I prepared it here, we have this disp underscore x, so you can copy and put it here for the name of the displacement in x direction, and the according expression, that is the expression I showed you on the slides. So you know where it's coming from. We just insert here, and we have to do the same thing. We have to do the same thing for the displacement component in y direction. We put it here, and we copy and paste the expression for the displacement in the y direction after rotation with angle phi. So, these local variables or definitions are local in the sense that whatever you can define, you can restrict to certain regions of the model. You can define it locally. So in order to do this, we have to change the entity level from entire model to domain, and we want to use this displacements for the square which has the origin at 0, 0. For the rotation of that one, of course, we have to modify something because it's shifted for the y. And the nice thing is, by definition now, the program knows this acts only on that square. So, for doing it for the other square, we just duplicate that variable 1, duplicate, and we want to have it for the other square, so we disable that one, and we need to modify in every position where we have x, we need to change to x minus x0. This is the shift of the coordinate system. So here in the original equation I had x and I put x minus large x0, and I should put this in brackets, round brackets. There is a second place where we have to do this for this y. There's another x. So we should change the x to x minus x0. Oh, if you do something obviously wrong, you see I copied the second time sign multiplication, then it gives you some color warning still. Because the bracket is missing. So, actually, next thing, we this time make the rotation not by any calculation, but we do it in the boundary conditions. So we go to solid mechanics and make a right mouse click, and there you can make a prescribed displacement. Prescribed displacement. Here it's displacement on the edge, which is the boundary in 2D, but we want to have the displacement for the whole domain. So we haven't done it very often, but we have to go here up to the domain boundary conditions. Where is it? There's something which acts on the whole domain, which is the prescribed displacement. So now we select what has to be displaced, which are actually the two squares, and we have to configure the type of displacement is not free, but we want to have it prescribed for the x direction and also for the y direction. And what we put in here, this is the x component. So we put our how was this? We may copy from here, just to be sure. We put this in here, and for the y direction, we change x to y. That might look a bit puzzling if you think about this, because we selected the two squares with the same term. So how it knows how to rotate this and how to rotate this is because we have this local variables. This is where he knows from which one he has to use with the minus x0 shift. This is a technique you can use for many other things. This is a special thing, but that's sometimes very useful. You can make the local definitions. Now, I mentioned it's possible to use the engineering strain, that's a simple definition, and the other one with the fancy name. This is set up in the material node, linear elastic material. If you open up, then under the term geometric nonlinearity, formulation from study, it seems also new. In former time that was called engineering strain, now it's called geometrically linear, okay. So we like to treat the left with engineering strain, so we have to remove the linear elastic material with engineering strain. We have to remove the second one. I cannot deselect. You know, this is one of the default nodes. You remember, it was there. So there has to be a material definition, so I cannot select it, deselect it. What I can do, I can duplicate this linear elastic material node. There can be a second one, and then I can distinguish. So let's copy, duplicate linear elastic material, just duplicate. And here I can remove the first one. I remove both, okay. Then I purposely selected the second one. And now the material gets overwritten. Here I selected the 2, but if I down in the sequence make another definition, it overwrites. So that's, I cannot remove it here, but if I make a second material node and select only that, it's overwritten. So that's the logic. And in the first one, I put it engineering strain or geometrically linear here. And in the second one, because I duplicated, it's also linear, so we should set it back to total Lagrangian, the green. They left the green away. Previously it was green Lagrangian strain. Anyway, let's have a quick glance at the equation. I'm not sure if it makes too much sense at the moment. Here is a definition for the strain that even looks different from what I wrote you down, but maybe I just want to let you notice this epsilon strain looks different with the engineering formulation than here, which is the correct one. You see at least there are more terms in here. For the moment we shouldn't bother about this. Let's do a computation now. Just to summarize what we did. We have two squares. They are both elastic materials. In one, we use the simpler engineering definition of strain, something like this. You pull on the rod and make it a bit longer. And on the other one, we take the fancy one, which is actually the correct one, which also works for large displacements. We move the squares both by rotating with the angle of phi. We used the rotation matrix to do that in that case. And now we want to see what properties we have after the rotation for the two types of strain definition. In study, there's another thing maybe to check for. Include geometric nonlinearity. Here it's preset, probably because we have one of them geometric nonlinear, meaning having the fancy definition of strain. In previous versions, you had to manually enable. Sometimes they change things, okay? Maybe because of physics control here. Let's try to make a simulation. Following feature encounter problem. undefined material property, Poisson ratio. I forgot to define the material. You see, we have to assign, of course, a material. In that case, we take something from the material library, structural steel, Struck. Let's see where we have Struck built in. So we just add to component. You are familiar with the three properties. We have a density, Young's modulus, Poisson ratio, this time from the library. Let's try to simulate again. Study compute. I can close the material node. Yes, here we go. This is Van Mises stress. We also could have a look at the strain. And color-coded, we see in the left one, where the engineering strain was used, we find a lot of strain just to get a feeling for how much you can actually click into that region, and you see it's giga, 10 to the minus 10. So we have giga Pascal stress, Van Mises stress, in the left one with the engineering definition, and in the right one, it's not exactly 0, but 10 to the minus 5. So that is some numeric fluctuation. So you see there is a dramatic impact if you use this simple engineering strain, because you would not expect to have a stress just by rotating it without putting any force on it. And it comes, I tried to explain before, that this is a displacement. Obviously, it provides some u. And if we calculate from the u in a too simple way the strain, and using E modulus, then we get a stress which is unrealistic. So the way out of this is to use a more elaborate way to calculate the strain. Still, we want to know how much it's stretched in the direction, not if it's rotated. Maybe to make it clear again, if this thing is rotated in that direction but stretched for some reason the same amount here, that should give the same stress and the same strain, independent if there is a rotation. But the rotation is part of the displacement, obviously. And we need only take into account the part of the displacement which works in the direction which is interesting. So this is only a statement of the problem. How this is attacked, I think, I don't know how you think about this, probably too tired, because this is again not so easy thing. Maybe I give you just some preview what you have to expect next Wednesday. Maybe it's also good to fill it this way. We can do it, we did a lot, and then maybe also we'll be done with the theoretical part. Probably then we do some more models and things. This is also on the way to state the problem, but a different way. The simulations you can do, I haven't put it here, no, I haven't. The first thing which I also recommend you to do is static simulation. Then we can do transient simulation, and we can do harmonic simulation. The simplest thing is static simulation. That means there's no time dependency. The partial differential equation, which actually is solved, looks like this. That is similarly not so difficult from what we discussed before, if we define this to be the stress. So how could you read that equation? You could remember with the Nabla operator and scalar operator, what is the source of stress? And you would give the answer, it's a volume force. So that makes sense. Huh? If there's some force, you get stress. I have to tell you, you have to bit carefully, because what we did so far, we applied that constant thing for what? For fields, vector fields. This is not really a vector, isn't it? because it's a tensor, so it's one dimension higher. The concept still works. You see, you can read it, makes sense, but you have to know this is not a vector, it's a matrix, or more precisely, it's a tensor. What it actually says that if you think about this 1D, then that would be like a pressure, force per area. And that would be in 1D the derivative in the x direction, so that means actually another length dimension, so it would be force per volume. This is actually what this is. So this is the balance of equation. It's nothing but Newton's law, the sum of all forces add up to 0. In a more fancy way because of the way mechanics is. So if you put this here, then you would say Newton's law add up all the force components add up to 0. That's the physics content of that equation, but because of material properties and the way material is mechanic, then it becomes a bit more complicated. Okay, that's the equation we have to solve. Dependent variable, the unknown to be solved for. Now where is it? Where is our u? The displacement field u, we talked about it several times, the thing you see if you set up the model and the visit, it's not directly seen here, but it must be hidden somewhere. We discussed already the relation between the undeformed material frame and deformed frame with that labeling. That's what we did in the exercise, but still, where is this displacement? I mean, the logic was we have this fundamental equation, and the equation provides us this displacement, but it's not seen here. Where is u? It comes in, we discussed it in a bit simpler way here. The Hooke's law, if the material becomes more complicated, then we don't only have the Young's modulus, we saw it, we have also Poisson ratio, and we can have more things, depending how the material behaves. But basically, it's still Hooke's law. So, okay, we could replace this stress with strain, then we have strain, have an equation for strain, but still, the strain is not displacement. And now I think we come to the part which maybe stop now, but just quickly, we can define such a transformation from here to here, and then we can rewrite it, and for 2D we can continue writing, and then we end up for a definition Green-Lagrange strain. Now they call it differently for the components of that. This now is expressed with respect to strain to displacement coordinates U, V, W. For the moment, it doesn't make sense. If it's linearized, means we have small displacements. What does it mean? We can neglect the square terms, because if it's small, the square of is small, and then we end up, which was historically called engineering strain. And here you see this is the derivative of the u component with respect to x. This is actually, in a way, what I wrote down here. And it works as long as you don't have too large displacements. We have a look at this a bit more in detail next lecture. I would suggest, in COMSOL it looks like this. I showed you these expressions before. Quickly, we may have a look again. Don't worry about this, not at the moment, also not next time, but I will finish explaining this, and then, we actually, again, with this demo we already did. I would say we have done enough for today. Have an enjoyable, relaxing afternoon. Goodbye. If you like to hear more about this, see you next Wednesday.